Hello. So what we're going to be going over today is my Electronics 3 term project, which is an audio clipper and compressor circuit. Basically, it's a three-stage circuit where you have a Bessel filter, which filters the audio or filters the signal to the audio range, and then a clipping circuit, and then a compressing and volume circuit. And in the next few slides, we're going to be going over what exactly all that is. So first, I'm going to explain each of the circuit blocks. So we're going to look at a block diagram of the signal path going through the circuit and kind of explain what each block does. And then next, I'm going to go over the experimental results that I gathered from building the circuit and gathering some data. After that, I've created a little clip where I've compared, so basically to demonstrate the way that because it's an audio circuit, the way that it sounds, to demonstrate what it sounds like just pass through, what it sounds like with the clipping on, and then what it sounds like with the clipping and compression on. After that, I'm going to discuss the results and do a brief conclusion. So the input to this circuit is a buffer, just to buffer the signal and prevent any sort of impedance, any sort of weird loading going on between the source and the circuit. That buffer goes into a Bessel filter, which we discussed a little bit earlier, but basically it filters it to the audio range, so around 20 to 20,000 hertz. And Bessel has better frequency or phase response characteristics than, say, a Butterworth. But in this case, it was only a two-pole bandpass, so that's kind of negligible. But from the Bessel to the clipper, in between them, there's another buffer. And then in the clipper stage, basically you have positive and negative clipping that are variable, controlled by a potentiometer, and they're independent as well. So you could clip just the positive voltages, just the negative voltages. And then after the clipper, there's a buffer between the compressor and the volume stage. And the compressor essentially, the volume is what you'd expect. It just boosts the signal. The compressor, what it does is, once the signal goes past a certain voltage threshold, the amount of gain past that threshold can be reduced to essentially kind of clamp down the signal to compress it. This Bessel filter is essentially a low pass and a high pass two-pole Bessel filter. Each of them just kind of cascaded for the band pass effect. The pass band is 20 hertz to 21,000 hertz, which is essentially, it's just the audio range. We want to limit to the audio signal to the audio range. There's not much more going on here other than just making sure that odd frequencies and high frequencies don't make their way into the signal path. The voltage clipper is a little more complicated. I labeled the buffers so that you can see, those are just, so the 4.7 micro cap and those are all, that's the buffer. But basically, it uses germanium diodes to clip the signal. So as the signal passes through, essentially what you have is the germanium diodes, which have a certain drop. So 2 in series is about 0.5, 0.6 volts because they have a low forward voltage. And then on the other side of that, there's an op amp with basically a voltage divider where the output of that op amp, say the whatever U12 or U12 and U17, the output is going to just be some DC voltage where that has a high resistance looking at it and then the big capacitance. So essentially it allows you to boost, whereas if it was just those diodes going to ground, the signal would always be clipped to 0.6-ish volts. But with this voltage boost, you can essentially raise the level of clipping so that you don't have to, so you can have variable clipping. And note that it's independent for both the positive and negative voltages. And then in the next stage, we have the volume and compressor circuit. And I already briefly described it, but basically, tuning the volume potentiometer adjusts the volume. Tuning the compressor potentiometer will reduce the gain past the threshold. And for the MOSFET, I chose to use the BS 170. It doesn't really matter that has a, when you use it in diode configuration, has a forward voltage of about 0.5 volts. But really, in either of these blocks, you could use pretty much any type of diode in there. I mean, they have different characteristics, so they sound different. And in this case, I chose the MOSFET for the compressor and the germanium diodes for the clipping, because germanium has, I guess, a softer knee, so it doesn't change from, if it's clipping, you would expect to see maybe a very smooth curve and then it flattens off harshly, like with a LED or something. But with the germanium, it has a softer curve, so it results in it's called soft clipping. And kind of the same thing with the MOSFET, but it has slightly different characteristics. But if we take a look at the results now, for the Bessel filter, I mean, all I did was just verify the frequency range, and it was a little, there's some tolerance errors in there, but 25 hertz, 21,500 hertz. Honestly, could have set the 21,000 hertz a little lower. I mean, that's the very upper end of the audio range, but really anything above like 14,000 hertz is just screeching. So it wouldn't have hurt to reduce that, but I just wanted to increase the range, just because, that's the official audio range. But the results for clipping, so on the left there, that's it with the voltage at the maximum clipping value. And as you can see, it almost matches the voltage of the input sine wave, which is the yellow wave, but it's flattened off at the top a little bit. And on the right hand side, that's it clipped all the way down. So you can clip it all the way down to pretty much, so the signal's almost nothing, which what I found is that, well, I thought it was going to be the left-hand side in that left-hand image, that was going to be effectively no clipping or turning off the effect. And the right-hand side was going to be the most amount of clipping. And sure, you'd have to boost the volume a little bit, but what actually ended up happening is that left-hand one, when you had the clipping at its maximum value but still kind of lopping off the very top, that actually resulted in the most distortion, whereas any of the lower voltages clipping more resulted in essentially just a volume decrease and a little bit of distortion if you cranked the master volume back up, which was not exactly what I expected to see, but I still got the effective distortion and the ability to turn it off by actually clipping more, so it's kind of just the opposite. And then this demonstrates the left and right. So basically how on the left-hand side, it's where just the negative side is being clipped. And to kind of make it clearer what's going on, I boosted the volume and compression all the way up to simulate kind of like a square wave so you can see it easier. But so the left-hand image is when the bottom voltage or the negative voltage is clipped almost all the way. And so you can see it kind of, if it was a square wave, it kind of changes the duty cycle, and then clipping just a positive voltage does the opposite. And the effect that this has is it changes the odd and even harmonics that it generates. So it's not always going to be a pure square wave, but you can tell the difference. It was hard to capture in testing, but when you're just playing with the circuit, you can tell the difference between having the positive clip-on versus just the negative clip-on. Yeah, so that was one interesting effect, and one of the reasons why I wanted to do variable so you can have it on or off. For the compressor stage, you can see on the left there, both of these images have the compression at the maximum compression value. It's kind of difficult to display without actually filming the way that it responds, because essentially when the compression's not on at all, the signal is just at its whatever its maximum value would be, and when it's on all the way, it's really clamped down almost to a flat response, like you can see in both of these images. Capturing the in-between things is really where you'd want to operate it, but it's hard to really capture it without video. But basically what these figures show is that one on the left is the maximum compression when the volume is all the way off, or I mean it's just so it's lowest, so that the output signal is the same as that the yellow input signal, and it clamps it down to about 0.5 volts peak to peak. On the right hand side, it's the same input signal but with the volume turned all the way up and the compression still turned all the way up. We can see how it clamps the signal down, making it more square-like. And there's a lot of range, like I said, in between that and the volume being all the way up, and it sounds kind of different all the way along that range. And then the volume control, this just shows the amount of gain that's possible. So that was an input signal, about 2 volts, and then you can see it's going almost to 10 volts. So I think that the ultimate, it's a 12 dB of gain. This being an audio circuit, I thought it would only make sense to do an audio demonstration that shows the difference between the effects as I've created them. So I created a little drum loop and then ran it through the circuit. The first time there's no effects applied. The second time there's clipping at the max value, and then the third time there's clipping and compression. So let's listen. So as we can tell, between the first and the second, the clipping adds a lot to the signal. There's a lot of kind of grit and bassiness added to it. It helps that the bass that I use for that, the kick drum, is pretty much just a sine wave. So the effect that you're hearing is very similar to the effect that we saw in the results section. The difference between the clipping and the compression, it's hard to tell what the compression does without the clipping, so I had them both going at the same time, but you can tell that it kind of reins that signal in from the clipping and kind of smooshes it a little bit. But there's definitely a difference between all three of them, and these are really just to show the max differences, but there's a lot of room for tuning in between those kind of values. In terms of discussing the results, the clipping behavior in practice was kind of unexpected, and I already covered what was different about that. The compressor range was not as broad with the practical signals, meaning that with the input signals as I had them, it was like when I was using the function generator, it was very clear like the compression had an effect all the way. You know, it could squeeze the signal all the way from being very huge volume all the way down, but in practice, you really couldn't tell the compression was on until the volume was almost going to rails, so like already distorted, and then you would crank the compression up and really only hear it at the very top of the knob. As for the filter, I could have used more poles, because basically I wanted to reduce the complexity for the PCB and for building it, but in retrospect I wish I would have made more poles on there and also lowered the cutoff frequency for the low pass filter to eliminate more of the noise, because as I found, the germanium diodes are pretty noisy, which I didn't really anticipate as being a factor, although it is well documented that they generate noise because they're kind of an inferior technology in a lot of regards, but for their current voltage characteristics they are desirable. And then an equalizer section would have added depth, significant depth to this, and initially there was a stage in between the filter and the clipping, which was a parametric equalizer circuit, which I intended to build and include in the PCB. But as I attempted to build it, it became quickly more complicated than I thought, and you're messing with positive feedback and negative feedback and just all sorts of weird kind of control systems, frequency stuff that when I was crunched for time, I thought, okay, if I can cut anything out of here, that's going to be the one to go because it's the most volatile. But in retrospect, it would have really added a lot of depth to this circuit where it was kind of lacking a little bit. But yes, in conclusion, the results that I found simulated versus experimental in terms of using like a function generator were very similar. Um, using when I was actually hooking it up to either my phone as an audio input or that drum machine or the synthesizer that I have, those have like impedance matching in them, which I believe was messing with the levels in a way that it was doing a good job to not let my circuit overblow, and make it super loud and everything. But in the same time, it was preventing the circuit, like the compression, from really having an effect until it was cranked all the way up. Um, I think that because ultimately I don't have a PCB design for this, which I regret, and I wish that I would have decided on a circuit earlier, locked it in, and then designed the PCB, because I ended up basically having a reduced version of the original circuit and no PCB, where I really wanted to have one or the other. But regardless, that my circuit can modify sound in a desirable way. I was pretty pleased with the results. That little clip kind of demonstrates pretty well what I was going for. But ultimately, I wish that it would have done a little more. But yeah, so that's what I did for my term project. I'm pretty pleased with the results all in all. Thank you.